So let's talk about one of the most powerful tools in all of science, the periodic table. And I want you to just completely forget about it being some boring chart you had to memorize in a classroom. Instead, think of it like a map, a predictive map to, well, the entire universe of matter.
I mean, what if you had a single document, a cheat sheet, that could tell you exactly how different substances are going to behave and react, just based on where they sit on the page? Well, that's literally what the periodic table does. And today, we're going to learn how to read it. All right, here's our game plan. First, we'll talk about why this table is the ultimate cheat sheet. Then, we'll learn how to actually read this elemental map. After that, we're going to uncover the secret of something called valence, explore 4 key trends that flow across the whole thing, and finally, use all that knowledge to predict chemical behavior. Let's dive in. Okay, so our goal here is not memorizing a bunch of elements. It's about understanding the absolutely brilliant logic behind the table's structure. Because once you get the why, you don't have to memorize anything. You can just predict. You know, every good map has rules, right? A key, a legend, something to tell you what's what. The periodic table is no different. So let's learn the 2 most fundamental rules of this elemental map: periods and groups. First up, we've got the periods. These are the horizontal rows that run from left to right. And the rule here is super simple. Every time you move down to a new row, you're just adding another energy level, or a shell, to the atom. So all the elements in period 3, they've got 3 energy levels. Period 4, yep, 4 energy levels. And so on. Easy enough, right? Next, we have the groups, which people often call families. These are the vertical columns that go up and down. And this is where the magic really starts to happen. See, elements in the same column act like a family because they have really similar chemical personalities and behaviors. And you can immediately see how this creates these distinct neighborhoods all over the table. Over in group 1, you've got the alkali metals, like sodium. These guys are explosively reactive. Then, way over on the other side in group 17 are the halogens, like chlorine, also super reactive, but in a totally different way. And then, at the very end in group 18, you've got the noble gases, like neon. They're the supremely unreactive cool kids of the table who don't interact with anyone. In every single case, their location on the map predicts their behavior. So why? Why do these families act so much alike? What is the secret sauce? Well, it all comes down to one single crucial thing: their electrons. Or to be more specific, their outermost electrons. These are called valence electrons. They're the ones living in the atom's outermost energy level. And let me tell you, they are the absolute star players in the game of chemistry. All the action, all the bonding, all the reacting, all the combining, it's all dictated by these guys. And this is the absolute key, the crucial point. Every single element in the same group has the exact same number of valence electrons. That's it. That's the secret. The alkali metals in group 1, they all have 1 valence electron. The halogens in group 17, they all have 7. And it's this shared number that gives them their family resemblance. Okay, so now that we get the basic geography and we know the secret rule of valence, we can start to see these beautiful, predictable patterns that just flow across the map, almost like weather patterns. These are the periodic trends. Let's start with something really fundamental: size. Just how big is an atom? As we move around this map, does the atomic size, or its radius, change in a predictable way? You bet it does. So the trend is incredibly consistent. As you move down a group, the atoms get bigger, but as you move across a period from left to right, they actually get smaller. Wait, smaller? How does that work? Let's find out. Okay, let's break this down. Going down a group makes perfect sense, right? You're adding more electron shells, kind of like adding layers to an onion. So of course it gets bigger. But going across a row is the really cool part. You're not adding any new shells, but you are adding more protons to the nucleus. This cranks up the positive charge, what we call the effective nuclear charge, which then pulls all those existing electrons in tighter, literally shrinking the atom. All right, next up, ionization energy. Now this sounds fancy, but it's really just the amount of energy it takes to rip an electron off of an atom. Is it easy to steal one, or does it take a lot of work? Now notice anything. This trend is the exact opposite of atomic size. It decreases as you go down a group, and it increases as you move across a period. And trust me, that is not a coincidence. And this just shows so brilliantly how all these trends are connected. Think about it. In a big atom, That outermost electron is way far away from the nucleus, so it's really easy to just pluck it off. That's a low ionization energy. But in a small atom, that electron is held in a super tight grip by that powerful nucleus, making it way harder to remove, a high ionization energy.
Let's move on to our third trend and see how this all keeps building. Electronegativity. This is basically a measure of an atom's ability to attract electrons towards itself when it's trying to form a bond. In other words, is an electron giver or an electron taker.
And what do you know? The trend is exactly the same as ionization energy. It decreases as you go down a group, and it increases as you go across. By now, you can probably guess why, can't you? Once again, it all comes back to size and the pull of that nucleus. A small atom with a powerful, nearby nucleus is like a bully on the playground. It's great at attracting and hogging electrons. But a big atom, with its nucleus far away and shielded, it has a much weaker pull. See? It's all connected. Okay, our final trend is reactivity, but this one has a bit of a twist. For metals on the left side of the table, their entire goal in life is to lose an electron, and since that gets easier to do in bigger atoms, their reactivity increases as you go down a group. But for nonmetals on the right, their goal is to gain an electron, and that's harder for bigger atoms to do, so their reactivity actually decreases as you go down. All right, this is the payoff. We've learned the MAPS rules, we've learned its patterns. Now, let's put it all together and use it to predict the future, or at least the future of chemical bonds. Here's how you do it. Just find any two elements. Then ask yourself, where are they on the map? If one is on the far left and the other is on the far right, they're going to have a huge difference in electronegativity. The bully on the right will just steal the electron from the weakling on the left. That's called an ionic bond. But what if the two elements are close together, like two nonmetals on the right side? Well, their pull is pretty similar. Neither one can win, so they have to share the electrons instead. That's a covalent bond. You can predict all of this just by looking at their positions. And that is the true power of this map. It isn't just some collection of elements. It is a predictive engine built on the fundamental laws of how atoms are structured. By understanding these patterns, you're not just learning chemistry, you're literally learning to read the code that builds our entire world. So the only real question is, what are you going to use it to understand next?